Hi, this is ET370 Lecture 11. This is going to be a three-part series. In the first part, we're going to review decimal or base 10, binary base 2, and hexadecimal base 16. And we're going to look at these two things on how to convert between binary to decimal and hexadecimal to decimal. We'll split it up. In the second part, we'll look at decimal to binary, decimal to hex, and in the last part, we'll look at binary to hex, hex to binary, because this is kind of a nice convenience here. And then the last thing is binary coded decimal. All right, but let's begin on the first three items here. So let's look at an unsigned 4-bit representation. We call it a nibble, right? So 4 binary bits. And remember, 4 bits to the 4, we can represent 16 decimal numbers, right? 0 through 15, right? Now in binary, what does that look like? Well, we have, 0, 0, 0, 0, 0, 1, and then 1 plus 1 is 10, right? 0, 0, 1, 0. Add another one, we get 11. And then if you add 1, you actually get to propagate this over, right? You get 100. And then you get 101, 110, right? And 111, 0, 111, right? And then we get 1000, 1001, 1010, 1011, 1100, 1101, 1110, 1111, okay? And let's just look at the pattern again. 0, 1, 0, 1, 0, 1 in this first column, double zeros, double ones in the second column, quadruple zeros, quadruple ones in the second and the third column, and so on, right? So you can see this pattern of every time you add a bit, you're doubling the number of unique combinations that you can represent. Now, base 16, very similar, except we've replaced the last 1, 2, 3, 4, 5, 6 digits with letters A through F, right? But this is base 16. This is binary for 16 numbers, and this is decimal for 16 numbers, right? And starting at 0. That's why we go to 15, 1, 1, 1, 1, or F. All right. So hopefully this is a good review of a 4-bit representation. Okay, so let's look at how would we convert binary to decimal, base 2 to base 10. So if you're given a binary number, how do you do that? Well, let's first look at base 10. Okay, so if we have a base 10 number, 78,523, and we learned from grade school, we got the ones place, the tens place, the hundreds, thousands, 10,000s, okay? And so each value, right, corresponds to a number multiplied by 10 to its place, right? And where the place starts with 0. So for example, the 3 here, wouldn't you guys agree that this is 3 times 10 to the 0, or just 3? But the 2 here is 2 times 10 to the 1, or 20, and so on and so forth. 5 times 10 to the 2, 8 times 10 to the 3, 7 times 10 to the 4, right? So ones place, tens place, hundreds, so on and so forth, right? And then what do? We just add it all up. That gives us the total number, okay? The same concept can be used for binary. When you see a binary number, 11011, for example, this is the ones place, the twos place, the fours place, the eights place, and the 16th place, and it keeps going. What does that mean? It's the same pattern that you have here. Okay, so if I take 1, I have 1 times 2 to the 0, right? Which is, and then I have, look, 1 times 2 to the 1, right? I have 0 times 2 to the 2, and 1 times 2 to the 3, and 2 to the 3 is 8, right? So on and so forth, okay? And then what do? You add it all up, and you get, in this case, 27. So 27 base 10 is the same as 11011. So it's kind of, I mean, I don't even know if I need to write out the rules, but let's write it out. Anyways, start with the rightmost bit as 0-digit order, multiply each digit by 2 to the digit order, increasing from right to left, and add it up to get the base 10 number, right? So what did we do? Let's repeat. 1 times 2 to the 0, 1 times 2 to the 1, 0 times 2 to the 2, which is 4 here, but this whole thing goes away because of the 0. 1 times 2 to 3 is 8, and 1 times 2 to the 4 is 16, and you add these up, 16 plus 8 plus 4 plus 2 plus 1 is 27, okay? So not too bad. Let's do a few more examples. So what's this? 1, 0, 0, 0. So that's the ones place, the twos place, the fours place, the eights place. So this is just 8. That's actually how you would represent 8. 1, 0, 0, 0 is 8. Okay. What about this one? Let's see if we can figure this out. The ones place, the twos place, the fours place. So this is 1, 4, and 2. So this should be 6, right? And if you did the low level calculation, 2 to the 0, 2 to the 1, 2 to the 2, it works out, right? Because this goes away. Not too bad here, right? So I hope you're seeing a very easy way of converting from binary to decimal. Just kind of think of ones place, twos place, fours place, eights place. This is, you know, the bulletproof way, right? Like blindly turn the crank. But I feel like if you know intuitively, oh, it's a 2. If I see a 1 1, that's a 1 plus a 2. That's 3, right? That's going to get you there a little faster and more intuitively in my mind. Okay, what about this one? So this would be a 1, right? Ones place, twos place, threes place, or not 3 place. This is a fours place, right? So this is a 1, a 4, an 8, and a 16. Okay. And then what is this? What's next after 16? 32, 64, 128. So you're going to add 128 plus the 16, 8, 4, and then 1, and then you're going to get 157. And like I said, that's a lot easier to think of it that way, maybe than doing the 2 to the, you know, digit order. It's the same result, but I think you guys get the point. Okay. All right, now what about fractions? Okay, how do you go from binary to decimal fraction? Now it's similar, but opposite to binary to decimal non-fraction. So what you're going to do is multiply each digit order to the right of the radix. What is the radix? The radix is that dot, the point, the decimal point, right? That guy, right? I hope I'm pronouncing it right. Radix, okay. 0.101. This is a binary number. And what if we want to increase it, convert it to decimal? Well, this is the halves place, the quarter place, and the eighths place, if that makes sense, right? And so we would do the same thing, but now we're going to go 1 times 2 to the minus 1, because what's 2 to the minus 1? A half. What's 2 to the minus 2? A quarter. What's 2 to the minus 3? An eighth, right? And so what you do is the same thing, except look at the difference. You have minus 1, minus 2, minus 3, and you're increasing from right to left, but you're putting a negative here, okay? And so in this case, 0.101 binary is going to be the same as 0.625 base 10, because I'm just adding up 0.5 plus 0.125. Okay, notice the 0 here, cancel that one out. Okay, let's do another example. What about this? 0.0101. Okay, so no halves place, that's gone, but I do have a quarter place and I have a 16ths place, right? So that's 0.0625 over here and 0.25 here. Add them together and I get 0.3125 base 10. So 0.101 binary is 0.3125 base 10. Okay, so not too bad. Okay, now how would we convert hex to decimal? Well, it's going to be the same thing as binary, except we're going to use 16 to the digit order. So if we have 94 base 16 and we want to convert that to decimal, well, you're going to do the same thing. You're going to take 4 times 16 to the 0 plus 9 times 16 to the 1. Okay, and then so we're going to add up 4 plus 144 in this case, because 9 times 16 is 144, and 4 times 16 to the 0 is, this is just 1 here. And so what do you get? You get 144 plus 4 is 148, so you get 94 base 16 is the same as 148 base 10. Okay, what about D3 base 16 to decimal? How do we do that? Well, 3 times 16 to the 0 plus D times 16 to the 1, but what's D again? Well, let's okay, so A, B, C, D. This is 10, 11, 12, 13. So it's going to be our 13 here. And so we got 13 times 10 to the 16 here. And what do we have? 208 plus 3. And so this is the equivalent to 11 base 10 is D3 base 16. Okay, let's do another example. So another example might be like FF base 16. FF base 16 is going to be, well, F we know is 15, A, B, C, D, E, F, right? 14, 15. So now it's 15 and 15 times 16 to the 0, 16 to the 1. What do we get? 240 and 15. Okay, right? 16 to the 0 is 1. Add them up and we get 255. FF base 16 is the same as 255 base 10. We might have seen this before. This is the equivalent for 8 bits, the max positive number you can see for 8 bits. So what do you have? 2 hex digits requires 8 bits, and we've seen this in the color code for neopixels here. Look at this, 255 and FF. Okay, so I'm hoping you're seeing the conversion between hexadecimal to decimal. All right, well, that concludes the first part of this lecture, and we'll see you in the next two.